Okay, so here's a lesson on equilibrium. Now, equilibrium is a concept that you probably understand conceptually, but in the chemistry world, of course, we make everything a little bit more difficult. So, equilibrium and reactions, they just mean that we have reactions, not all reactions, but some reactions can be in equilibrium. Um, if we were in the classroom, I would show you a bottle, so a bottle of water that's half full. If we have that bottle of water that is half full, you'll notice that on the top of it, up there at the top, you can do this at home too. Take a bottle of water, let it sit there for a while, and you'll notice there's condensation on the top of the bottle, in the space at the top. Now, what happened there was some of the water that was at the bottom started to evaporate, and because you have the bottle closed, that water is going to condense at the top of the bottle, and as it condenses, it's going to stick to the sides, and then it'll run back down into the bottom. And so what we have there is called a phase equilibrium. The amount of water that's evaporating is the same as the amount of the water that is condensing on the inside of the bottle, and it's returning. So the level of the bottle, the level of water inside the bottle doesn't change at all. So we have what's called an equilibrium. An equilibrium reaction is a reaction that is a reversible reaction. So reversible reactions occur not all the time. There's only certain ones that will do that. You'll see this double-headed arrow. It looks kind of like that. Sorry. You'll see a double-headed arrow like that. The most common one that you'll see is this one here. It's called the Haber process. I told you this will show up frequently. The Haber process is a very famous reversible reaction because what happened is we are able to change nitrogen and hydrogen into ammonia. All right. And as it turns out that this is an exothermic reaction. We know it's exothermic because heat, this kilojoules per mole, 91.8 kilojoules per mole, that's energy, and it's being produced. It's on the product side. The Haber process is a process where nitrogen gas reacts with hydrogen gas in the presence of an iron catalyst at very high temperatures and very high pressures, and it produces ammonia. Um, that's just the reaction. This is a very famous reaction. This reaction shows up a lot on the Regents exam. This is an equilibrium reaction. That's one of the reasons it shows up. So an equilibrium reaction means the nitrogen and hydrogen can change into ammonia, but at the same time, ammonia can change back into nitrogen and hydrogen. So the reaction goes in both directions. And you might be thinking, well, what's the point of that? Well, the point of that is it's a reaction that can be reversible and reversed. And you can also, because it can be reversed, it can be forced to go in one direction or another. Um, Equilibrium, the term equilibrium, that just means that the rate of the forward reaction is equal to the rate of the reverse reaction. So as nitrogen and hydrogen are changing into ammonia, ammonia is changing back into nitrogen and hydrogen. And so what happens is the concentrations, the amount of nitrogen and hydrogen and the amount of ammonia, they stay the same unless you do something to it. And again, you're probably asking, well, what's the point of that if you're not producing anything? It's just like that phase equilibrium that we had in the bottle. The amount of water evaporating is equal to the amount of water condensing. So what happens is the amount of water inside that bottle doesn't change at all. And so that's an equilibrium. All right. Another example I like to use is the line outside of a bathroom. All right. So here we see a bathroom. Here's the men's room. Usually, you got a whole bunch of line of guys standing outside the bathroom. Well, let's imagine for a moment that we have 5 bathroom stalls in there. Okay. And so what happens is there's one guy in each bathroom stall, and as he uses it and he's done, he comes back out. He comes out, and another guy goes in. So the rate, and this is called a system in equilibrium, because the number of guys going in is only going to be one, because one guy comes out, one guy goes in, one guy comes out, one guy goes in. That is a system in equilibrium. Now, the number of guys on the outside is not equal to the number of guys on the inside. On the outside, you may have 50 guys standing there in line, whereas on the inside, there's only 5 stalls, so there's 5 guys in there. All right. So the rate, this is a system of equilibrium because the rate of exchange from outside to inside is the same as the rate of exchange from inside to outside. That is a system in equilibrium. Okay. And we'll just go with that for now. So an equilibrium expression is a mathematical representation of these. So mathematics can be used in this. We will not use this in Regents chemistry nor honors chemistry, but it will be used in AP chemistry. And it's a mathematical expression that shows how your reactants and products are related in terms of concentration. Chemistry uses the square brackets, these things right here, square brackets. They are used to denote concentration. So when you see this, when a chemist sees square bracket NH3 square bracket, they read that as the concentration of ammonia. And as you learned, concentration is the amount of moles per volume per liter. Concentration is moles per volume. We can do that. We can do that for gases. We can do that for liquids, and we can do that for aqueous substances. We can't do that for solids because the concentration of a solid is, well, it's a solid. All right. There's not moles per liter. All right. So concentrations are only used for solids, from gases, liquids, and aqueous substances. And so therefore, when you write an equilibrium expression, which you will not have to do, when you write an equilibrium expression, it's only going to include gases, liquids, and aqueous substances. That's the only things that are included. There's nothing below that. Okay. Now, this is from the Old and Busted Review book. I want to talk about a couple of questions here. You can read these pages on page 142 and 136. 146, they're in topic 8. You may want to read that for a little bit more in depth. There's also some questions in New Hotness. But right now I want to talk about these questions real quick. So question number 18 says, which factors must be equal when a reversible chemical process reaches equilibrium? Well, if we talk about a system in equilibrium, that simply means that the rate of exchange from one side to the other side and back is the same. So the mass of the reactants and the mass of the products, that they are not the same, okay? They are not equal. They won't change, but they're not equal. The rate of the forward reaction and the rate of the reverse reaction, that is equal. That's the important part right there. The rate of the forward reaction and the rate of the reverse reaction, that is what you have in an equilibrium. The mass of the products and reactants could be different. Concentration of products, they're not going to be equal, right? Their rates will be the same, but their concentrations are not equal. And activation energy has nothing to do with it. So again, equilibrium just means the rate of the forward reaction and the reverse reactions are equal. Another 2 questions right here. Let me put this up here so you can kind of see here. So it says a solute is added. This is a phase equilibrium, a physical equilibrium. A solute is added to water and a portion of the solute remains undissolved. So over here we have a beaker and it has water in it, and there's some stuff and there's some grit sitting on the bottom of it. It says when equilibrium between the dissolved and undissolved solute is reached, the solution must be, well, what that's saying is as this stuff dissolves into solution, some of the stuff that's in solution is going to undissolve and precipitate back onto the bottom. That is a solution that is in equilibrium, and those are saturated solutions. Saturated solution means as solute dissolves, solute undissolves and precipitates out, and that is a saturated solution. Saturated solutions are equilibrium. We've talked about saturated solutions in the last couple of days. When a chemical reaction is at equilibrium, the concentration of each reactant and the concentration of reactant must be, they are constant. That means there's the concentration of the reactant and the concentration of the products, they are not changing. Doesn't say they're equal. They're not equal, all right, but they're not changing. They're constant. The concentration of the reactant, the concentration of the product are constant. Another question is like this. Which description applies to a system in a sealed flask that is half full of water? That's exactly what I was talking about before. A bottle of water. All right, so in a bottle of water that's sealed, I mean, it's got the cap on, what's happening? Well, as the water evaporates, some of that water that's in the vapor phase is going to condense and change back into water, so it's going to condense. So only evaporation occurs? No, evaporation is going to occur and condensation is going to occur. All right, so both evaporation and condensation occur, and that's what you have in an equilibrium. Okay, just changing the colors here. The second question says, an open flask is filled with water at 25 degrees Celsius. Phase equilibrium can be reached after, well, the only way you can get a phase equilibrium, a physical equilibrium, is if you cap it. Otherwise, what's going to happen? You have to think about it. You have a bottle of water, all right, and there's no top on it. What's going to happen? Well, all that water is going to evaporate eventually. But if you want to get that equilibrium, you have to cap. The flask has to be stoppered. You have to cap that bottle. Otherwise, it's just going to run out, right? So the phase equilibrium is only reached if the cap is on. And I think this is the last question. So solution equilibrium always exists in a solution that is saturated. Saturated solutions are at equilibrium. That's where that whole idea of the solute is dissolving as the solute in the solvent is undissolving and precipitating out. That is a solution equilibrium. Solution equilibriums, phase equilibriums, chemical equilibriums, they're all the same. There's some questions here regarding change. So you guys are asking me, well, wait a minute. Why would we want something at equilibrium? Well, Le Chatelier, he was a science dude, and he said if a stress is applied to a system at equilibrium, that system's going to adjust to compensate for that stress to reestablish the equilibrium. So let's go back to our good old friend here, the Haber process. In this one, if we did nothing, it would establish an equilibrium where the amount of nitrogen and hydrogen remain constant and the concentration of ammonia will remain constant. But that doesn't do us any good. We want to make ammonia. So what they do is they apply a stress to the system. All right. So what they'll do is they'll increase the concentration of nitrogen, increase the concentration of hydrogen. And what that does is, because this side now is bigger, it forces the equilibrium in the forward direction, and it produces more ammonia. Also, what they would do is they would siphon off any produced ammonia and reduce. So this side of the reaction is decreasing, this side of the reaction is increasing, and as such, the reaction proceeds in the forward reaction because it's always trying to reestablish a equilibrium. It tries to make, well, my concentration of ammonia keeps going down, my concentration of nitrogen and hydrogen keeps going up. I got to make an equilibrium, so it's going to go in the forward direction. Similarly, we could also remove heat from this reaction, right? Pull this out of the reaction, and that would also conceptually force the reaction to go in the forward direction. However, that doesn't actually work in the real world because this reaction has to happen at high temperatures and high pressures. So this kind of helps the reaction occur to go the forward reaction. So that's Le Chatelier's principle. If a stress is applied, it's going to compensate for that stress, and in doing so, what's going to happen is it's going to make the reaction move in the direction to reduce that stress. This, I got a toilet paper roll. Okay, just a cardboard insert. And what I did is I took a balloon, a purple balloon, I put it inside and I blew up the balloon. So now part of the balloon is sticking out on this side and part of the balloon is sticking out on this side. So you got part of the balloon sticking on the left, part of the balloon sticking out on the right. All right, I tie it off, and so now I have a balloon. That balloon is a contained system at equilibrium. If I were to suddenly squeeze on the left side, what's going to happen? Well, yeah, the right side's going to get bigger. So what I did is I had a system at equilibrium. I applied the stress. I squeezed here on the left side. And what happened is that system reestablished its equilibrium by moving to the right, and it made the right side bigger. All right, so think of it that way. So if I have a system here at equilibrium, I squeeze on this side, it's going to happen. It's going to go over to this side. It's going to move to this side. All right, that is a system equilibrium. If I were to do the same thing on the other side, it would have a similar effect. Two buckets in equilibrium. So we have two buckets here. We have a bucket on the left, bucket on the right. They're connected by a hose. All right, they have the amount of water in each one is constant. So if you pour, the water in this one has the same level as the water as this one. Yes. But if I were to pour water into the left one here, what's going to happen? Well, what's going to happen is here in the hose, water is going to go from this left side over to the right side to maintain that equilibrium, right? So if I pour water on this side, it's going to move, it's going to shift to the right. If I were to pour water into the right side, water is going to shift over here to the left to maintain that equilibrium. And that's what an equilibrium is. If I pull water out of the right side, water is going to move from the left to the right. So it's going to shift from the left to the right. So stress is applied on this side.